Everyone, my name is Pragya Srivastava. I'm a student of BSc Semester 6 regular. My college roll number is 225070 and my topic for presentation is dual space, covariant and contravariant order of mixed tensor. So let us first understand vector space. Let V be a given set. We shall call elements of V as vectors. Let F be a field whose elements will be called scalars. We say that Vf is a vector space if the following conditions are satisfied. First condition, there exists an internal binary operation plus on V called vector addition such that V plus is an abelian group. Hence, first subpart is for all alpha beta gamma belongs to V, alpha plus beta in brackets plus gamma is equals to alpha plus beta plus gamma in brackets is associative law. Second part is there exists a 0 belongs to V such that alpha plus 0 is equals to 0 plus alpha is equals to alpha for all alpha belongs to V. Here 0 is called identity or 0 vector in V. Third is for all alpha belongs to V there exists a beta belongs to V such that alpha plus beta is equals to beta plus alpha is equals to 0. Beta is inverse of alpha. Now fourth is for all alpha beta belongs to V such that alpha plus beta is equals to beta plus alpha. This is commutative law. Now the second condition is there exists an external binary operation called scalar multiplication such that lambda belongs to F, alpha belongs to V, lambda into alpha belongs to V. The scalar multiplication satisfies the following axioms. First is for all alpha beta belongs to V, lambda belongs to F, lambda alpha plus beta is equals to lambda alpha plus lambda beta. Now the second point is for all alpha belongs to V, lambda and mu belongs to F, lambda plus mu alpha is equals to lambda alpha plus mu alpha. Third is lambda mu into alpha is equals to lambda mu alpha. Now fourth is 1 alpha is equals to alpha. 1 is unity element of field F. Now basis of vector space. So let Vf be a vector space, a set S alpha 1 alpha 2 to alpha n of vectors of V is called the basis of V if the following two conditions hold good. So first is the set is linearly independent, that is lambda 1 alpha 1 plus lambda 2 alpha 2 plus lambda 3 alpha 3 2 lambda n alpha n is equal to 0. Here lambda 1 is equals to 0, lambda 2 is equals to 0 to lambda n is equals to 0 where lambda 1, lambda 2 to lambda n belongs to F. Second is for each alpha belongs to V, alpha can be expressed as linear combination of vectors of S. We say that S spans V. Now let's discuss dual space. M subscript MR is the space of contravariant vectors. Let mu be a function mm over R such that for all lambda V belongs to mm, AB belongs to R. Now mu A lambda plus BV is equal to A mu lambda plus B mu V. Then mu is called a real valued linear function. This mu here, this is called real valued linear function. mm over R. Let mm star be the set of all such real valued linear functions. We define vector addition on m subscript n star as follows. For all mu delta belongs to m subscript m star, lambda belongs to m subscript m, mu plus delta into lambda is equals to mu lambda plus delta lambda. This is the first equation. Define scalar multiplication between m star plus r and r as follows. For all mu belongs to m star, lambda belongs to mm, a belongs to r, a mu into lambda is equals to a nu lambda. This is the second equation. Now it can be shown easily that m subscript mr is a vector space under vector addition and scalar multiplication defined by equation 1 and equation 2. Equation 1 and equation 2 were these I have written here. So we call m subscript m star r the dual space of m subscript m r. Okay, so this is m subscript m star r is the dual space of this m subscript m r. Now we will discuss contravariant vectors. So let Vr be a vector space and let M belong to V. We denote by C superscript infinity M the set of all differentiable functions in the neighborhood of M. A tangent vector lambda at M is function on C infinity M mapping functions of C infinity M into real numbers and satisfies the following axioms. For all f and g belong to C infinity M, first is lambda f plus g is equals to lambda f plus lambda g. Second is lambda fg is equals to fm lambda g plus gm lambda f. Third is lambda af is equals to a lambda f. Here a belongs to R. Now covariant vectors. These were contravariant vectors, now covariant vectors. So we call elements m subscript m star r as covariant vectors if mu belong to m subscript m star and lambda belongs to m subscript m. Mu lambda is a real number. Mu lambda is equals to mu lambda I ei is equals to lambda I u ei. Here lambda I, the I here is superscript and the I with e is subscript. Putting mu ei is equals to mu I is equals to 1 2 3 to n. Mu lambda is equals to lambda superscript I mu subscript I. This is the first equation. We take n covariant vectors. E superscript I belongs to m subscript m star as E superscript lambda is equals to lambda superscript I. This is the second equation. And E superscript I is E superscript I into E subscript j is equals to delta ij. Here I is superscript and j is subscript. This is the third equation, where delta ij is equal to 1 if I is equals to j, and this will be equal to 0 if I is not equal to j. I have written here. We can write equation 1 as mu lambda is equals to mu subscript I e to the power I lambda. Therefore mu is equals to ui e to the power I, which can be written as mu1 e1 plus mu2 e2. We are putting the values of I here, that were 1 2 3 to n. So values of I were 1 2 3 to n. Okay, so we will put these values here, mu1 e to the power 1 plus mu2 e to the power 2 to mu n e to the power n. So arbitrary covariant vectors mu belongs to m star can be written as linear combination of e to the power I. So this spans m star r. E to the power I spans m star r. Now we will discuss the last topic, that is mixed tensors. So let us consider n square quantities a I j of vector a dash in a coordinate system x1 x to the power 2 to x to the power n. If these n square quantities are transformed to n square other quantities a dash ij in another coordinate system x dash 1 x dash 2 to x dash n, according to the transformation a dash ij is equal to a subscript b superscript a delta x dash I upon delta x to the power a into delta x b x to the power b upon delta x dash j dash is not here. Then A dash is called mixed tensor of rank 2 where Aij and A dash ij, these are the components of mixed tensor. Aij and A dash ij are the components of mixed tensor. This was the end of my topic. Thank you so much.